In this video, I will discuss about London equation. So, in the banner of London equation, we will first define London equation. There are two type of London equation. Okay. Then we define London penetration depth. Then we define coherence length. Okay, and lastly we discuss about Ginsburg London parameter. And this parameter is very important to difference between superconductor like type 1 superconductor and type 2 superconductor. So this parameter plays an important role. Okay, so we will discussing in a well manner. So let's start our video. So age London assume that a superconductor has two type of electron. Okay, first one is normal electron and second one is superconducting electron. Okay, or it is also be called as super electron. Normal electron and superconducting electron, and this superconducting electron is also be called as super electron. Okay, they use free electron and their equation of motion is given by m dv vector by dt is equals to minus of e vector, and this will be equation 1. Here v is drift velocity, m is electronic mass, and E is electric field. But we have superconducting supercurrent density and this is defined by JS vector. We know current density is equals to NE v vector. Okay, so superconducting current also be the same equation, but here N will be changed to Ns because this is the number of total number of superconducting electrons. So we here the subscript is S, Ns. Okay, Ns E minus of Ns E v vector. Here minus sign we involve because we use electrons, so charge of electron negative, so this will be so their minus sign will be involved. Okay, so and this is equation 2, and here Ns is total number of superconducting electrons. So now we simply differentiate equation 2 because we need dv by dt, and if we differentiate this equation 2 we got dv by dt, and we using simply this equation 1. Okay, so now we differentiate equation 2. So now we differentiate equation 2 and we get dou js vector by dou t. This is the equation ns e, okay, minus of e dv vector by dt. Okay, and this will be okay. Now we using simply equation 1, and we substitute the value of dv vector by dt. Okay, so this will be equals to, here dv vector by dt is equals to minus of e vector divided by m. Okay, so minus minus will be plus, and this will be ns e square e vector by m. So this will be equation 3. So equation 3 celebrated as first London equation. Now we simply taking curl both side of equation 3 and we get, okay, so now we simply taking curl of equation 3 and we get, so this will be curl of dou js vector by dou t, and here these are the constant term ns e square m, so this will be curl of e vector. Okay, so and this is equation 4. But according to Maxwell equation, we have we now we using Maxwell equation, okay, in this place. So but according to Maxwell equation, we have curl of e vector is equals to what? That is equals to minus of dou b vector by dou t. Simply we substitute this value and we get from equation 4, simply substitute this value on equation 4 and we get, so what we got, curl of dou js vector by dou t is equals to minus of ns e square by m dou b vector by dou t. Okay, ns e square by m dou b. Okay, so this equation also be written as dou js vector by dou t plus ns e square m dou b vector by dou t is equals to 0. Now this equation also be written as curl of js vector ns e square m b vector is equals to 0, or ns e square by am b vector is equals to 0. Therefore curl of js vector is equals to minus of ns e square m b vector, or it will be and we know what we know. B vector, this is magnetic field, applied field, it is also equals to minus of mu naught edge vector. So we can write, if we substitute this value, then we can also got mu naught ns e square edge by m. This is the other form of curl of js vector. Okay, js is supercurrent density, and this will be equation number what? Earlier we got equation 4, so this will be equation 5, which is equation 5 is called as second London equation. Okay, now so we define two type of London equation. Now we define London penetration depth. Okay, so London penetration depth. So now we discuss this. Okay. So simply we using Maxwell field equation, and what we know about Maxwell field equation, that is about, according to Maxwell field equation, we have what? Curl of b vector is equals to mu naught js vector. Now simply we taking curl both side, and we get, taking curl both side, and we get mu naught curl of js vector. Okay, now we substitute the value of curl of js vector with help of second London equation. What we got from second London equation? Curl of b vector is equals to mu naught. Here we substitute the value of curl of js vector. So this will be equals to, now we use this value actually. So ns e square by am b vector. So minus of ns e square by am, ns e square by am b vector. Okay. Now simply we using back cap rule. So now using What is back cap rule? So here I discuss you back cap rule. Back cap rule is it is for cross product, actually, cross product rule, actually. Okay, cross triple product. So if A cross B cross C cross, then it is equals to B divergence of C, grad of B divergence of AC, and this is here, this is equals to here back, and this will be cap C A dot B vector. This is called back cap rule. So now we simply this formula we substitute here, and we get here B. B is the del operator. So B AC A dot mean divergence, okay, and minus of cap C AB. So this is equals to minus of mu naught ns e square by m b vector. Okay, but we know this value will be 0. Okay, with according to Maxwell equation, we also this we know that divergence of b vector is 0, so this will be 0. Okay, so b vector, and this will be divergence square, grad square. Okay, so grad square b, and minus minus will be cancelled, so this will be mu naught ns e square by m b vector. Okay, because is 0. Okay, so here b vector by lambda square, where now we define a term, actually, with help of this equation. So if we compare these two equations, we can write lambda as m by mu naught ns e square. Okay, and root over this new term is called as London penetration depth, called as London penetration depth. This will be equation number, this will be equation 6. Okay, now we simply draw the graph of London penetration depth. Okay, so London penetration depth, the plot of London penetration depth is like this is magnetic field, and this will be London penetration depth, and the curve looks like this. Okay, this is the graph of London penetration depth. So our next topic is coherence length. Okay, so coherence length, London penetration depth is a, so what I understood, London penetration depth is a fundamental length that characterizes a superconductor. So an independent length is called coherence length, and it is denoted by xi symbol, actually, Greek symbol. Okay, this is xi. So now intrinsic coherence length is defined as epsilon naught, sorry, xi naught is equals to h cross vf by 2 Eg. Here Vf, here Eg is energy gap, and this will be equation 7 also, and Vf is electron velocity at Fermi surface. This will be electron velocity at Fermi surface, and psi naught is intrinsic coherence length. Intrinsic coherence length. So this is about coherence length. Okay. Now our last topic is Ginsburg London parameter. Okay. So, and it is symbolized by K actually. Okay. This is Ginsburg London parameter. Uh, Ginsburg London parameter is simply the ratio of lambda and xi. Lambda means London penetration depth, and xi means coherence length. Okay, so this is the simply ratio of these two term. Okay, this Ginsburg London parameter K distinguishes type 1 and type 2 superconductor. Okay, this parameter played an important role uh, to distinguish of superconductor or to define superconductor. Okay, for type 1 superconductor, type 1 superconductor means soft superconductor. Here K is less than 1 by root 2. For type 2 superconductor or a hard, or you can say hard superconductor, here K greater than 1 by root 2. So this is about Ginsburg London parameter. So hope you enjoy this video. If you enjoy this video, then please like, share and subscribe. Okay, so thanks for watching.